So in this section of the notes, we're going to start talking about wires and how they're affected by magnetic fields. So we'll look at the force on a wire, and then a little later we'll actually look at how wires themselves can create magnetic fields, which is what we were trying to test in that mess of a quote-unquote lab that we started on Friday that hopefully will get fixed up on Monday. But for right now, we'll talk about the force that some wire that has a current running through it would experience due to a magnetic field. So electric current, we already talked about this a little bit. It's just a bunch of charges that are moving around. So if you have a wire that's carrying a current, it could be subject to a force when it's in a magnetic field, depending on how the current and the magnetic field are oriented with respect to each other. So the only thing that's a little bit different here when we're talking about the current in a wire, we don't want to use units of Q and V. So our magnetic force was QV cross B. We could essentially break this wire situation down into Q and V, but it would get really messy really fast. So we have a different way that we can talk about Q and V here. Oh, not an image. I want to add some text. So instead of talking about Q and V, so if we looked at Q times V, what would the units for that look like? Well, Q would be coulombs, V would be meters per second. So if we try to split that up a little bit, we know that a coulomb per second is actually something different. Coulomb per second is equal to an ampere, which we know we use amperes to measure current. And then the meter part here, what could we use meters to talk about when we are talking about wires? Here it's going to depend on how long the wire is, so we will use that for L. So if we substitute, instead of QV, we substitute in I and L, then when we talk about magnetic force on a current carrying wire, we would have I times L times B. So instead of QVB, ILB. And then of course we'll have our sine theta. So I just replaced the L here with a cursive L. Usually when you see the equation, you'll see it with a cursive L, only because the I for current looks so similar. So when you're writing out that equation, you probably want to use a cursive just to help you keep the variable straight. Oh, I jumped ahead of myself. Alright, so QV goes to I and L. And then down here, this is where we want to put our equations. So if we replace Q and V, we get F equals, I'm just going to copy and paste. So we have a different way to write the magnetic force equation when we're talking about a current carrying a wire. So theta here is the angle that the wire makes with the magnetic field. It's no different than before, where the velocity made some angle with the magnetic field. So we can still do the same thing, determine the direction of the force by using right hand rules. So instead of our index finger being V, our index finger is going to be I, the current. And we kind of already did that before. We broke it down though, so instead of talking about I, we said, well, electrons are moving this way, so we have to flip it, and then since it's electrons, we flip it again. And a few of you did pick up actually that wouldn't it just be a lot easier to just keep your finger in the same direction instead of flipping it twice? And essentially that's what we're doing, and now you know why we're allowed to do that. Alright, example time. So in this figure above, we have a magnetic field of 4 times 10 to the minus 5 teslas, and it's being applied locally to just one part of a circuit, so just that bright side. So we have a 5 ohm resistor in the circuit, a potential difference of 30 volts given by that battery, and the length of the wire where the magnetic field is applied is 2 meters. So we want to figure out what is the magnetic force just on that stretch of wire. So we know that we have to get to F equals I LB sine theta. So let's start going through here and figuring out what some of these different pieces are. So the current, we're not given a current, but we are given enough pieces to figure out what the current is. So we have to go back to Ohm's law and use 30 volts and 5 ohms. So we have I equals V divided by R. So 30 volts. And we need to divide that by our 5 ohms. So now we know we have a current of 6 amps. So length is pretty easy. That one's given. It's 2 meters. B is also given to us 4 times 10 to the minus 5 teslas. And then theta. There we go. Alright, the theta, we're not given a theta. It doesn't mention anything about parallel or perpendicular, but we can kind of assume from what's going on in this diagram, the wire looks like it's going straight up and down, and B looks like it's going straight into the page. So we'll assume that theta equals 90 degrees. So when we go to try to figure out what our force is, we have I times L times B, and then times sine of 90, so just 1. So we plug all that into our math, we have 4.8 times 4.8 times 10 to the minus 4 newtons of force. But since we're not asked only for the magnitude, we also have to figure out the direction. What direction will this wire experience a force in? So here we're going to apply our right-hand rule. So we have our current. Our current flows from the positive to the negative side. So our current is going up here. So current goes up, our index finger points up. Our magnetic field goes into the page, so our fingers should point into your computer screen. So you stick your thumb out. Which way is it going? It's going the thumb points off to the left. Sorry, I thought I caught an error, so I had to pause really quick. The other thing that I'm looking at while I go through and fill these out has an error. It says that the current is flowing down through that section of wire, but it's actually flowing up here. So current up, B into the page, thumb points off to the left. So when we get a complete answer for our force, we'll have 4.8 times 10 to the minus 4 newtons to the left. So that's how a current carrying wire can experience a force from a magnetic field. They're also able to generate one, and that's called Ampere's law. So we've discussed that so far in this unit how a magnetic field can affect a moving charge. So it exerts some kind of force on a charge that's moving. But we haven't discussed the opposite of that. So a moving charge, some kind of current, can actually generate a magnetic field. There's no time like the present, so let's get to it. The magnetic field created by just one single moving charge is really actually pretty complicated. But when we think about the case of a really, really long straight wire that has some steady current, it's pretty simple. And it's probably something you will definitely run into when you take the AP test. So Ampere's law tells us that to figure out the magnetic field strength in this situation, we would have B equals this constant mu 0, and you'll see down below mu 0 is called the permeability of free space, and we'll get to that a little more in a second. So we take this current, or this constant, multiplied by the current, and we divide that by 2 times pi times r. These Greek letters are killing me. I have to go find them every time I want to paste one in. Alright, so B equals permeability of free space multiplied by the current divided by 2 pi r. This 2 pi r is going to be really, really important in a second. So hopefully it's something that's familiar to you right now. But more about this permeability of free space. In a vacuum, it has a constant value of 4 pi times 10 to the 7th newtons per ampere squared. Kind of basic way to understand this constant is just like how much resistance is there going to be to create these fields and forces in whatever kind of environment you're in. So here in a vacuum, it should be the easiest. So it just tells us how hard it's going to be to create this field, I guess. So not so important to memorize the equation exactly because, obviously you have your equation sheet with all of the equations on it, but it's really important to note that the strength of the magnet is going to be, for one, proportional to however much current there is. So proportional to the amount of current. If your current goes up, then the strength of the magnetic field will go up. So proportional to the amount of current, and 2, and it'll get weaker the farther away you get. So inversely proportional to the amount of distance from the wire. So it seems pretty common sense, right? More current, higher magnetic field. You get really, really far away, it should be a pretty weak magnetic field. Alright, so since we're kind of doing an inverse thing here, where instead of looking at the field's effect on a moving charge, we flipped it around, so now we're looking at how does a charge generate a magnetic field. We have to come up with a slightly different right-hand rule. This one is a little bit easier if you feel like the first one might have been a little bit harder. So for this one, all you're going to do is pretend like you're trying to grab onto the wire in question. So if you held the wire, if you held the wire with your thumb in the direction of the current, then your fingers will curl around in the direction of the magnetic field. Make that just a bit smaller. So we have an example down below. The current is moving off to the right. So we should pretend like we're going to just reach into the computer screen and wrap our hands around this wire with our right hand, making sure that our thumb points off to the right so that it's in the direction of the current. So if we try to grab onto this wire with our thumb pointing off to the right, then our fingers would have to go into the computer screen underneath the wire. That's why there's all these X's here. So at all these points down below, it's going into the computer screen. And then if we try to grab it, we'd have to curl our hands around and they would come back out toward us over top of the wire. So that's why it's out, 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 out. So we're making these circles with our hand when we try to grab onto that wire. So that's why all of these look like a circle and why in our equation we have a 2 pi r. So we make all these circles. Every circle then would have the same value of magnetic field. So the closer in you get, the smaller the circle is, the stronger the value of the magnetic field will be. Right? If you divide by a small number, so small circle, you'd wind up with a bigger magnetic field. And then another example here, we have now our wire going into the page. So we want to try to grab onto it. Our thumb has to point into the page, and you can see how we curl around in this clockwise fashion. And then same thing here, this value for magnetic field is weaker than this middle one and weaker than the inner one. Alright, one more example, and then that is it for plain old magnetism. So here we have two parallel, long straight wires that are carrying a current I, and they stand a distance r apart. We want to look at what force does one wire exert on the other. Okay, so we are looking for here a force. And we know that when we talk about wires, so force is equal to I times L times B. We do have a sine theta, but we'll see later that we won't need it here. So let's start looking at what we have here. So let's say we're looking at the top wire. We want to know what is the force exerted on the top wire. So the force in the force equation, this I is actually for the top wire. So we use the current running through the top wire, and the magnetic field is generated by the bottom wire. And the length 2 would be however long the top wire is. Okay, so what do we know? We know that the current running through the top wire is equal to I. All we really know for the length is that it's really, really long, so we can't worry about that just yet. And then the magnetic field that it's in, well, that's going to be generated by the bottom wire. So we know the equation for that. I've got to copy and paste again. Alright, so mu naught I over 2 pi r. And let's go through here. So mu naught as a constant, we can't really do anything with that. This I is the current running through the bottom wire, but we know that it's the same thing. They both have current I. 2 pi numbers can't do anything there. R, so the spot where we care about the magnetic field generated by this wire is actually a distance r away from it. So we don't have to worry about changing r, that's already what we want. Alright, so now we're in a better place to talk about the force here. So we have I times L, too many letters, and then we're going to replace this B with this B. So let's just do this. So it's looking kind of ugly right now. Let's clean it up a bit. We have I times I, right? They're both carrying current I. So that'll get us I squared. Our L and our mu0 don't change, so we still have those things. Oh my gosh. And then we have nothing to do with our 2 pi r, so that just stays right the way that it is. And that would get us the magnitude of the force, so that would be how big it is. So because these wires are so long, and we're not specifically told how long they are, it might be more useful to just talk about a more general case of force per unit length. So depending on how long it is, so I'm just going to divide both sides by the length of the wire. Our force per unit length would be equal to this value. And then we could figure out which direction it would go in. So we have a magnetic field generated by this wire. If we use our new right hand rule, we point our thumb off to the left and try to grab that bottom wire. So you reach underneath into the computer screen. So anything underneath goes into the page, anything above, if we curl our fingers around, would come out of the page. So that means the magnetic field here is pointing straight out of the page. So if we try to do our old right hand rule to figure out what direction the force would be in, our current runs to the right, so index finger to the right. B is out of the page, so your middle finger should be pointing at you. This is a tough one. Oh, so that would make your thumb point down. So when you have two wires running parallel to each other, they would actually be attracted toward one another. So we'll say toward the other wire. So remember, this question was kind of general. We look specifically at the top wire, but we want a general answer that would answer this question. So the top wire would experience a downward force, but it's not quite general enough for this question. So the answer that we want to go for is just kind of a general, it's going towards the other one. And then that wraps up just plain old magnetism. Next we'll get into a little bit more about kind of this generation of magnetic fields when we talk about electromagnetic induction. So remember here, important formulas, we have magnetic force. This one you probably won't ever use. This is the one that's going to be really important for you, F equals Q VB sine theta. Radius of a circle, remember we mixed centripetal force and magnetic force. Then we got into magnetic force on a current, and we just did that in the example, and a magnetic field generated by a current we also did in the last example.